I've never beaten 2048 in my life before, so I built an AI to destroy it for me. After 3 failed AIs, 2020 generations, and more than 20 hours of compute time, it did it. Okay, let me show you how I started this project in the first place. So as you can see, I'm really terrible when it comes to future planning. Some could say embarrassingly bad at it. I've been playing 2048 for quite a while now, and I've never in my life gotten close to beating the game. The highest style I think I've ever gotten was 1024, and that was because the stars were aligned for me on that day. But outside a perfect day like that, I was a constant 512 towed guy. So I had an idea, a possibly stolen idea, but an idea nonetheless. You know the popular saying, if you can't beat them, create a machine to destroy them. So here's the game plan. Step 1. Build the 2048 game. Step 2. Build an AI to play the game. And step 3, which is our last step, use my AI to challenge the world's highest human speedrun record. To answer the question, are humans better than AI when it comes to playing strategy games? Well, let's find out. I started by going to my old GitHub project when I initially built the game. I already planned to use the old project instead of rebuilding the game from scratch. But well, what could I have expected from my old GitHub project? My code was a mess, the AI was very bad, and it was barely playable. I couldn't obviously use that to train my AI, so I had to build the 2048 game from scratch. But this time, instead of using Tkinter, an old GIA library for Python, I used Pygame, which is built specifically for building games in Python. And the difference between them is crazy. I added extra little things like a timer and a move counter. And with that, step 1 of our game is completed. Onwards to step 2, building an AI to play the game. Now this is where things get interesting. What I failed to mention earlier on was that I wasn't just going to be building one AI to beat the game. I was going to build 3 AIs to beat the game, then pit them against each other in an ultimate showdown. And the winner could go ahead to compete with the world's fastest 2048 speedrun record. Buckle up. So let's start with AI algorithm number 1, Monte Carlo Tree Search. Monte Carlo Tree Search, or MCTS, is one of those algorithms that sound way more complicated than it actually is. Let me set a timer for 30 seconds and try to explain it under 30 seconds. Ready? Let's go. The basic idea of MCTS is that it just tries stuff, lots of stuffs. For every possible move, up, down, left or right, it simulates hundreds of random games to see what happens, and it picks whichever move that leads to the best average outcome. You could say it's the ultimate what if machine. What if I move left? Let's simulate 500 games of me moving left and see how it turns out. That's MCTS for you. So I started using this algorithm to code an AI that plays 2048. And let's just start by saying MCTS is freaking slow because of the sheer number of simulations I had to do. And plus I'm using Python for this. It's crazy how it can spend 30 seconds on just a move. And after everything, the AI is still crap. Because for it to be good, you have to increase its number of simulations, which you will normally waste your entire day if you're not running it on a good hardware or using a faster programming language. But sadly, if that was enough to make me give up, I won't be coding in the first place. I'm sure you guys have seen those programming language ranking video where a cartoon guy ranks programming languages by how fast they are. And I'm sure you guys have had questions when you saw Python on the list of fast programming languages. Well, Python itself isn't fast, but its libraries are, because most of them are built with C++. So what I just had to do was to swap out the sections of the code that handles the simulations and replace them with some Python packages like NumPy and NumBar. And these libraries really increase the speed of the AI, so now I can make it run more simulations for it to be smarter. Alright, attempt 1 of this new improvement. Okay, first try, did worse than expected. Attempt 2, I see progress, we almost hit 2048. Third time is the charm. But in this case, I guess it's not. 4, ends the same way. Okay, attempt number 5, this is it, I can feel it. There's 1024, there's another 1024 right next to it. Yes! Let's freaking go! There it is, we did it! Okay, that's our first win. But here's the thing, it took 5 attempts, and even with the optimization, it's not exactly really the fastest. Each game takes close to a minute. Monte Carlo has proved it's possible to beat 2048, but is it the best approach? Let's try something completely different. Something that doesn't rely on random simulations at all. Something that learns. Let me introduce you guys to NEAT. NEAT, also known as Neuroevolution of Augmenting Topologies. If Monte Carlo was about controlled randomness, NEAT is about evolution, natural selection, survival of the fittest. But instead of animals, we're using neural networks. Here's how it works. Start a timer. You start with a population of completely random neural networks. You could think of them as baby AIs that know absolutely nothing. You let them play the game, and most of them will be terrible. But the few that make good moves out of pure luck, you keep them. And as for the rest, you them all. You're lucky if you get to survive and reproduce with each other, which in layman terms means the neural networks are coupled with a small random mutation, and over thousands of generations, the population gets filtered out, and only the fittest remains, which are then used to play the game. This is basically programmers trying to play God in their spare time. My implementation was bad cause I'm not really trying to play God. I started by training my algorithms for 200 generations and the highest was 256. I decided to bump it up to 500 generations and it could barely reach the 526 style. So I tried retraining it again, but this time for 1000 generations, and its performance wasn't that different from the 500 generations one. It's really annoying because it took me hours to train this algorithm for 1000 generations. Now imagine how many times it takes for 2000 generations or even 5000 generations with my laptop. I'm sure there's potential in this algorithm, but I don't think I can wait long enough to find out. So if any of you guys are curious on how well it can perform, check out the code on my GitHub and try training it on your own hardware. But as for me, that's how far I was going to go with pure NIT. Alright, this time I tried combining the NIT algorithm with another algorithm. It's actually a search algorithm called Expectimax search. How this algorithm works combined is that the NIT acts as an AI intuition, a neural network trained through hundreds of practice games to instantly recognize what makes a 2048 board strong, like keeping big tiles in the corner or maintaining empty spaces, while Expectimax serves as its planner that thinks 2 or 3 moves ahead by simulating every possible swipe and random tile spawns that follow. During actual gameplay, Expectimax explores future board states by asking, what if I swipe up, left, down, right? And whenever it reaches the end of the simulated move sequence, it consults the NIT network to judge how promising the future board looks. And with that way, Expectimax makes up for the short-sightedness of the NIT algorithm. But enough talk, let's see it in action. User frequently reaches the 1024 tile and occasionally reaches 2048 with the same number of generations as the pure NIT approach. This clearly shows the downside of evolution: randomness. NIT is good for games where the strategy is complex and hard to define mathematically, like fighting games, platformers, games with physics, but 2048 is a puzzle, so there are ultimate strategies that are mathematically better. And this brings us to our third algorithm, the one I should have started with: Expectimax, the algorithm that actually thinks. Unlike Monte Carlo, which simulates random futures, and unlike NIT, which evolves randomly, Expectimax actually calculates the mathematical optimal move based on game theory. Here's the core idea behind Expectimax. This algorithm helps the AI play 2048 by looking a few moves ahead. For each possible move, up, down, left or right, it imagines what the board might look like after that move and what random new tile appears. And since the new tile is random, it doesn't just hope for the best, it calculates an average score across all likely outcomes. If the random tile is 2 or sometimes even 4. At the end of each imagined sequence, it scores the board based on simple rules like more empty space equals better or big tiles in corners equals better. Finally, it picks the move that leads, on average, to the best looking future board. And that's how Expectimax algorithm works. Let's see my final implementation of this algorithm in action. Yeah, let's go. We reached 2048 on the first try. That's freaking awesome. But there's a trade-off. The more intelligent you want the algorithm to get, the slower it becomes. So I'll build 3 completely different approaches to solve the same problem: Monte Carlo's random simulation, NIT evolution learning research, and Expectimax logical planning. And throughout the video, I mostly ran these algorithms once or twice, but that's not really a good way to tell how well they truly perform. There's only one way to truly find out: the ultimate showdown. 100 games per algorithm, same game, same condition, same hardware. May the best AI win. While this run, let me explain what we're actually measuring. First, win rate. How often does the algorithm actually achieve 2048 tile? This is the most important metrics that tell if they can actually beat the game. Second, average maximum tile. Even if an algorithm doesn't win, how high does it typically get? Yeah, consistency matters. Third, peak performance. What's the highest tile each algorithm has ever reached? This shows the ceiling of each approach. And the last metric is average time per game. Speed matters. If an algorithm is smart but it takes forever, that's a real limitation. Alright, let's go back to the time lapse. Okay, all 100 games are done for each algorithm. Time for the final results. Drum roll, please. Here they are, compared to one another. Here are the individual stats for each of them on the screen. Now for what we have all been waiting for, the world record speedrun of 2048. Can my AI beat it? The current record is held by a flashy human called Weg, and the record is 1 minute, 34 seconds and 956 milliseconds. And obviously from that stats, my Expectimax model can be the cap out of them. So that's why I'll give this record holder a handicap. I run my model only once, and I'll use that one game to compare to the record holder. Sounds fair, right? Well, this result is mostly built on trust with you guys, so 59 seconds, 1 millisecond. That's how long it took a machine to be the world's best player. Sad to say, but if you're ever competing with a machine, just give up. Don't even think twice, just give up. And if AI is coming for your jobs, don't fight it. Just give up and become a door-to-door salesman. It was really fun working on this project. For those who want the code, it's in the description. Make sure to like the video and subscribe. And don't forget to add comments on your code and this video. Thanks for watching.